Hi guys, this is Mrs. Foy, and this is a quick screencast about the ionic size of atoms and a pattern or a periodic trend that we see. So how does the atomic radius compare to the ionic radius? And you should be able to answer that question at the end of this little screencast. So the foundation of being able to figure out why atoms act the way they are is something called Coulombic Attraction. And if you haven't already done an activity in class that would help you understand Coulombic attractions, you soon will. But the basics is that protons repel protons, right? Like repels like. And electrons are going to repel other electrons. We know that. And protons and electrons are attracted to each other. And so there's going to be a force there. And we're going to see a trend of these Coulombic attractions that we see going down a column or a family in the periodic table, and also across a period or a row or an energy level in the periodic table. So let's look at the trend going down a column or family. So here are the alkali metals. I've got good old lithium, I've got sodium, and I've got potassium. So as you see these atoms going down the periodic table, I would want to write something else here. Let's look at the energy level. So lithium is in the second energy level, or the second period. Sodium is in the third period, or third energy level. And potassium is in the fourth energy level, or fourth period, fourth row. Let's look what's happening here, all right? So obviously we are adding more protons and electrons as we go down. So we look at lithium. Lithium has an atomic number of 3. That means there are 3 protons and 3 electrons. Sodium has an atomic number of 11, so that's 11 protons and 11 electrons. And potassium has an atomic number of 19, so that means 19 protons and 19 electrons. And you're like, okay, duh, Mrs. Foy, I got this. But let's look where those electrons are added, okay? Every time we add more protons, guys, we're adding it to the nucleus, right? But when we add new electrons, we are adding them every time we go to a new energy level or a new period or a new row. We are adding electrons to the outer energy levels, right? As dictated by the quantum mechanical model. And so what happens is these valence electrons, and I should say all we care about are the valence electrons, guys. That's basically it. We only care about the ones on the outer energy levels because they're the ones that are going to react and make bonds. So what I want you to do now is I want you to look at the Coulombic attraction. This is review if you've already done this activity in class. I want you to look at the distance between the valence electron, between the valence electron and the proton in the nucleus. Do you see how this is getting larger and larger and larger distance, right? Because the energy level is further and further away from the nucleus. And so what's happening, as we see in this arrow here, the Coulombic attraction is getting weaker and weaker on those valence electrons, all right? And so that's really important to see. So as we go down a column or down a family on the periodic table, we see a weaker attraction for the protons on the outer electrons. And so what happens is they're going to kind of spread out because that Coulombic attraction is getting weaker. So now let's look at what happens when you go across a period, right? When you go across a period, which is also an energy level or also a row, you are keeping those valence electrons in the same energy level. So let's look at sodium, aluminum, and chlorine. If you look at your periodic table, this is all going to be in the third period or third row or third energy level. And let's look what's happening here. Yes, I'm adding protons, right? So sodium has 11, aluminum has 13, and chlorine has 17. And so this would be 11 electrons, and this would be 13 electrons, and this is 17 electrons because these are neutral atoms, right? But now let's look at the distance, all right? When I add that 11th electron or the 13th electron, right? What is happening is based on the quantum mechanical model, the valence electrons that I'm adding are going in the same energy level. So the distance to the nucleus is the same, right? That's an important point. Meanwhile, back at the ranch, I am adding more and more protons to my nucleus. And so I am getting a greater pull as I go across a period. I'm getting a greater Coulombic attraction because I'm adding more protons at the same, I'm adding more protons and electrons, but the electrons are in the same distance each time. And I'm adding more protons as I go across a period. And so I'm going to have a greater Coulombic attraction as I go across a period. So let's review very quickly atomic radius, right? So atomic radius is just a fancy way of saying the atomic size. And I'm measuring from the center of the nucleus to where the outer shell of electrons are, those valence electrons that are buzzing around in those clouds, and we don't know exactly where they are, but we can see basically the edge of the shape of that, of those electron shells, and that's where we're going to measure it from. So what happens when you make an ion? So we know that we can make a cation by losing electrons. And we know that we can make an anion by gaining electrons. So a cation is going to lose electrons, anion is going to gain electrons. And that is going to cause the ionic radius to change. I'm not talking about the atomic radius anymore. I'm talking about the ionic radius, all right? And so if you need more help with the atomic radius, periodic trend, or ionization energy, or electronegativity, this is not the screencast for you. I'm just going over ionic radius right now. So let's look at cations first, and let's look at our good old friend sodium. So sodium has 11 protons, right, in the nucleus, and it has 11 electrons that are spread out in various energy levels as dictated by the quantum mechanical model, right? And this is going to have a certain size, right? So this is 186 picometers. This is going to be the radius, all right? But let's say I lose an electron, which sodium is happy to do. It's actually more stable as an Na+1. Now I have 11 protons and only 10 electrons. And you can see immediately what's going to happen with the Coulombic attraction, aren't you? Think of this as like a tug of war. I have 11 things pulling on 10 things. Here I had 11 positive things pulling on 11 negative things. This is going to be zoop, right? Those 11 protons are going to really pull in those 10 electrons, and the size is going to get smaller. So cations are always smaller than their respective neutral atom. So now let's look at, we talked about lithium. Lithium is going to be a metal. It's going to want to lose electrons, and we talked about why that's smaller. Now let's talk about an anion. All right, let's talk about good old chlorine. So chlorine has 17 protons and 17 electrons in a neutral atom. But let's look at what happens when chlorine becomes chloride. Okay, so once we make the nonmetal an anion, we call it chloride, right? This is called chlorine, and this is technically chloride, all right? So really, this should be chloride, right? Spell it right. There we go. So what happens here? Well, I still have 17 protons, because if it's 17 protons, guys, it's chlorine, okay, period. But now I have 18 electrons, okay? And so I have 17 protons pulling on 18 electrons, and those electrons don't like each other. They want to try to be as far apart as they can. And so what's going to happen is it's almost like the chloride atom loosens its belt a little bit, and these electron clouds spread out a little bit. And so the anion becomes larger than the atom, the neutral atom that it came from. And so what's going to happen? Well, as I go across, let's look at, here are just the regular atom sizes, okay? And you can see I get smaller. I get smaller as I go across a period because of the Coulombic attraction is actually getting stronger, as we talked about earlier. But what is going to happen is that within that trend, each time I make an anion, the anion is going to be larger than the neutral atom, okay? So anions are going to be larger than their respective neutral atoms. And I really like this slide because this really kind of sums it all up, all right? So let's look at this. Parent atoms are brown, okay? So let's look at the metals first, all right? So I can see that the ion colors are in red. So the cations, I'm seeing the size in red, okay? And look what happens every single time. Do you see that the brown circle is a lot larger than the red circle? And that is just showing me that every single time the cation is going to get smaller. And you can see that that is also very significant in the +2 metals and in the +3 metals, okay? And so I see the atom size getting larger as I go down. That has to do with the atomic radius trend, but I see that the cations are always smaller. Now let's look at the anions in turquoise, all right? And I see the parent atom again is brown, and I see the size, right? I'm looking this way as I'm going across here, and I see, yeah, the atoms are getting smaller as I go across, but look every single time at the anion. Do you see how the anion in turquoise is always larger than the parent atom? And so I hope this has been helpful for you. My goal with this is not just to memorize this, but to understand it. You have so many things in your brain that you have to memorize. It's really good if you can kind of reason it out. And if you understand the basics of Coulombic attraction, you can do just that. So I hope this has been helpful, and I'll see you in class.